Hello, my name is Kevin Nguyen, and this is my lab 2, motion of a falling object. So for the introduction, our goal is to observe the motion of a falling object. So to do this, I use a tracker and a computational model. And we did one with gravity only, and the other with gravity and drag force. Then we're going to compare the predicted position versus time with the computational model, and then at the end, we're going to answer some what-if questions that talks about terminal velocity and an object being thrown downwards. So the laws used in my experiment, we used Newton's second law, which is final velocity equals initial plus F net over mass times delta t. The initial velocity is 0 since we dropped it, but force net is not 0 because velocity changes. And this is because there's some interactions with the object, which is the weight and drag force. Then for the tracker, I set up the coordinate system at the center of the paper ball, and the ball has a length of 0.0635 meters for the diameter, and that's what I use for the calibration. And this is going to be the position versus time graph. As you can tell, it goes down the slopes because it's going to go in the negative y direction as it drops down. So for the computer model with the gravity only, I measured the mass of the ball in kilograms. The initial position is negative 8.3 times 10 to the negative 4, which is going to be the initial position of the tracker, the same. We start at 0, delta t is 0.001, a small delta t to make it more accurate. Gravity is 9.8, and j hat is going to be 1 in the y-axis, since we're only looking at the y-axis. It's going in the y direction. B is 0 since there's no drag force. And then our weight is mass times gravity times j hat, and that's going to be our force net. As you notice, it's going to be negative since it's going to be going down, negative direction. And this is going to be our Newton's second law, and we're going to use that to update our position. And this is going to be the model of the ball at the origin. It's going to drop down, and this is going to be our force of gravity magnitude. And you can see this position versus time and the velocity versus time. And you notice the velocity versus time is a constant linear slope down. So it's changing velocity at a constant rate. This is going to be our model, experiment versus model on the graph. So the model predicted that it would fall further than it did. So this is the model and this is our experiment. As you can tell, there's a large gap between each. And this shows how much of impact drag force is on the paper ball. So drag force is making the ball go down slower. And this is the computer model for gravity and the drag force. It's basically going to be the same, except the only difference is we're going to have a b now. And to calculate the b, we're going to use our final position and time of our experiment data, which was 0.7 seconds and negative 1.406 meters. Then we're going to use these two equations, the force of gravity and then force of drag, which is b times the magnitude of the speed. So magnitude of the velocity squared times j hat. And we're using magnitude because the equation is b times speed squared times j hat. We use j hat to turn it back into a vector. And we did trial and error plugging in different b's and printing the time position of the ball at the end. And b will affect the force net and impact the position of the ball. You do this until the position and time equal each other to find b. And then, which I end up finding is 0.003733. And then force net is equal weight plus force of drag, and that's everything else would be the same. And this is gonna be our model. So you can tell this is the air resistance, drag force, and this is our force of gravity. Our velocity versus time is different though. It's not constant rate anymore. It's slowing down here as time increases. This is gonna be our position versus time. This is gonna be our graph. So you can tell this is our model and experiment position. This is a much better comparison than the other model with only gravity. But there's still a large gap in here because this is because of the proportionality constant, which I was talking about before, the b. So we went through trial and error at the last position and time, but this is when there's a large difference in time, and our data is most likely incorrect by then. And then this is both of the graph models together. As you can see, the gravity is over here, and then the gravity and drag is right here, which is way closer to our actual experiment data. So what if? Which model predicts the terminal velocity? Terminal velocity is when drag force and force of gravity are balanced. This is when net force is 0 and there's no acceleration. So the only model that has drag force would be the second one. So the model of drag force and gravity would be able to predict the terminal velocity, and you would write this in code by finding when the drag force and the force of gravity will equal each other, and then you get the time, and then you can calculate the velocity at that time. But now what if the object is thrown down? So if it's thrown down, the downward force would be higher, and it would change the time it would take to reach terminal velocity. So it would change when the drag force and the force of gravity will equal each other, and the force of drag increases with increasing speed. But the terminal velocity would still be the same. So the only factors that affect terminal velocity would be mass, surface area, and acceleration due to gravity, which is not changed when the object is thrown down. As you tell, this is the velocity versus time for both of them, drop from rest. So you see the terminal velocity started being constant at negative 2.8 meters per second. And then when you throw it down at initial velocity of negative 1, you see the terminal velocity is also still constant around negative 2.8 meters per second. And for the aeroscale that I used, you notice that the magnitude at the end are balanced, so showing that it's going to be constant velocity and reaching terminal velocity. And for the arrow length, you can't just set it to the weight or the force of drag. You can't do this because these numbers give magnitude. Remember, the different units are not to scale, so we determine how long to draw each arrow based on the amount of force. So for the weight force, it was mass times gravity, which was 0.03 newtons in my experiment. And I chose an arrow length of 2 meters for each, 0.03 newtons, and then so you divide the meters over newtons, which is going to be around 70 meters per newtons, which is going to be our arrow scale, and then you multiply weight times your arrow scale, and I also did the same thing for force drag to get them in the same magnitude in units. And this is why they look similar, and that's it. Thank you.